Welcome to ExplaQuiz channel. Today we are looking at large language models in a very gentle and practical way, without getting lost in jargon or hype. We will start from basic ideas like artificial intelligence and machine learning, and slowly build up to how systems like ChatGPT predict words. And yes, quizzes will come along the way to test how well you are following. Let us begin with the most basic term, artificial intelligence. In this article, AI is treated as something artificial that behaves in a way we would call intelligent if a human did something similar. That does not mean it has human understanding or magic powers. It simply means the behavior looks useful, engaging, or non-trivial from the outside. A nice example is computer game bots. Many of them are built from plain if-then rules, but if they keep the game interesting, we may assume they are far more advanced than they really are. Once we understand the mechanism, the mystery reduces. So one key idea is this. AI often feels magical only until someone explains the trick properly. Machine learning is a way of creating behavior from data instead of handwriting every rule. You collect examples, use algorithms to detect patterns, and produce a model. That model is not the real thing itself. It is a simplified version of a complex phenomenon. Just like a model car resembles a real car but cannot replace it, a language model resembles patterns in human language without being a human mind. When we say large language model, the word large mainly refers to scale. Human language has enormous variety, so modeling it requires a huge number of learned settings and a lot of memory. That is why systems like GPT-3 and GPT-4 need serious data center hardware to train and run. So that covers the basics of AI, machine learning, and why these models are called large. Now that we've covered AI and ML basics, let's test what we've learned so far.
Here's quiz number 1. See if you can get it right.
Question 1. According to the article, what makes something count as AI? The correct answer is, it behaves in a seemingly intelligent way. The article defines AI by behavior that a person might reasonably call intelligent. It does not require a brain-like structure or consciousness. Question 2. Why can simple game bots still seem intelligent? The correct answer is, their behavior keeps users engaged. Even simple if-then systems can appear smart if they behave usefully and avoid obviously silly actions. Question 3. What is a model in machine learning? The correct answer is, a simplified version of a complex phenomenon. The article compares a model to a model car, useful and similar in some ways, but not a full replacement for the original. Now let us move into neural networks, but with a very friendly metaphor. Instead of thinking about brains, the article asks us to imagine electrical circuits. Inputs send signals forward, outputs trigger actions, and many connections exist between them. At the start, if everything is connected without careful tuning, the result is chaos. The self-driving car example makes this easy to picture. The car has proximity sensors in different directions, and outputs control steering, braking, and acceleration. If every sensor influences every action strongly, the car may brake, accelerate, and turn at the same time. Clearly, we need some way to control which signals matter more and when they should activate. In the metaphor, resistors control how easily energy flows, and gates decide when enough signal has arrived to pass something forward. In real neural networks, these adjustable settings are called parameters. Training means changing those parameters bit by bit so the network behaves more like the data suggests. Backpropagation is the algorithm that helps make those tiny improvements over many repeated adjustments. Deep learning is basically an extension of this idea. Instead of only simple gates and weighted paths, we add more layers and more internal calculations in the middle. Those hidden layers transform information before it reaches the output. Now that we understand the circuit metaphor, the basics of neural networks and deep learning are in place. Now that we've covered neural network basics, let's test what we've learned so far.
Here's quiz number 2. See if you can get it right.
Question 1. In the car metaphor, what do the outputs represent? The correct answer is, steering, braking, and acceleration actions. The outputs are the robotic actions the car can take, such as steering, braking, and accelerating. Question 2. What is the role of parameters in the neural network metaphor? The correct answer is, they adjust how signals flow and activate. Parameters correspond to things like resistor strengths and gate behavior, which shape how the network responds. Question 3. What does backpropagation mainly do in training? The correct answer is, make small changes to improve behavior. The article explains backpropagation as a method for making tiny tweaks that move the network closer to the behavior shown in data. A language model applies the same learning idea to text. It takes words as input and tries to predict what word should come next. For example, after once upon the word time should get a much higher probability than something odd like armadillo. So the core task is not memorizing one sentence, but learning patterns of likely continuation across lots of human writing. The article introduces probability here, but in a very simple way. The model is basically assigning scores to possible next words based on the words that came before. Higher score means more likely in that context. Then this process repeats again and again, one word at a time, which is how longer text gets generated. Here is where things become tricky. A language model may need to consider tens of thousands of possible words, both as inputs and outputs. If we connect everything directly in a naive way, the number of connections becomes absurdly large. That is why language models need smarter internal representations, rather than one giant brute force lookup system. Instead of keeping every possible word fully separate at every stage, models compress information into smaller internal spaces. These hidden representations allow the system to carry useful patterns forward without drawing impossible numbers of connections. That is one of the big reasons large language models can work at all. So that wraps up the basic idea of a language model as a next-word prediction system built from learned internal representations. Now that we've covered language model basics, let's test what we've learned so far.
Here's quiz number 3. See if you can get it right.
Question 1. What is the main job of a language model in this article? The correct answer is, predict the next likely word. The article frames language modeling as guessing an output word based on the input words that came before it. Question 2. Why is time more likely than armadillo after once upon a? The correct answer is, it fits common language patterns better. A good language model learns common continuations from text data, so familiar phrases receive higher probability. Question 3. Why can't we simply connect every word directly in a huge naive network? The correct answer is, there would be far too many connections. With very large vocabularies, direct full connections become impractical, so models use more efficient internal representations. So today you learned how AI can be explained step by step, how neural networks are trained, and how language models generate text by prediction. Hope you did well on the quizzes and found the topic much less intimidating now. If you enjoyed this, do like, share, and subscribe for more interactive learning videos.